Buenas tardes a todas y todos. Es un gusto darles la bienvenida al coloquio del día de hoy y presentar formalmente a nuestro nuevo colega, el doctor Daniel Winnie Corona, quien se incorpora a nuestro instituto como investigador asociado C en el Departamento de Estructura de la Materia. Daniel es originario de la Ciudad de México. A los 4 años emigró con su familia a California, donde cursó la licenciatura en física en la Universidad de California en San Bernardino, obteniéndola con honores. En la misma institución concluyó también las licenciaturas en matemáticas y en economía. Posteriormente realizó sus estudios de doctorado en la Universidad de Indiana bajo la dirección de Adam Stepaniak, antiguo colaborador de Marcos Moschinsky. Su trabajo doctoral se centró en el análisis de amplitudes en decaimientos de 3 cuerpos y en procesos de fotoproducción. Más adelante llevó a cabo estancias postdoctorales en la South China Normal University y en la Universidad de Bonn, en Alemania. La llegada de Daniel representa un fortalecimiento claro de una de nuestras áreas estratégicas, estrechamente vinculada con el propio nombre de nuestro instituto, la física nuclear. En particular, la espectroscopía hadrónica y el estudio de la interacción fuerte. Su línea de investigación se enfoca en la dinámica de QCD, la espectroscopía de hadrones y el estudio de estados exóticos, con contribuciones en revistas de primer nivel y una participación activa en grandes programas internacionales asociados a Jefferson Lab y el futuro Electron Ion Collider. Además, cuenta con una trayectoria destacada en docencia y en la formación de estudiantes, particularmente en cursos avanzados en mecánica cuántica y teoría cuántica de campos. Para el ICN, su incorporación es particularmente valiosa, pues refuerza nuestra presencia en física teórica de partículas y nuclear, amplía nuestras posibilidades de colaboración internacional y enriquece el entorno académico tanto para estudiantes como para colegas. Daniel, te damos la más cordial bienvenida a nuestro instituto. Estamos seguros de que tu trabajo y tu visión científica serán una aportación importante para nuestra comunidad. Sin más, es un honor presentarles a nuestro nuevo colega, el doctor Daniel Winnie Corona. Muchas gracias.
Hola, gracias. Mucho gusto estar aquí. Como dijo Alfred, desde los 4 años he estado viviendo en los Estados Unidos y vida en inglés, entonces si hablas conmigo más de 2 minutos, notas que tengo un acento de gringo, aunque nací aquí. Por la misma razón, mi habla va a estar en inglés, porque para esta primera plática en frente de ustedes no quiero arriesgarme a decir algo incorrecto. Entonces, here we're going to switch and start. I'm also going to put a timer so I don't accidentally talk for 2 hours. Okay, so the central theme that I want to talk about is Regge theory, what it is, how I use it. It's not but it's certainly the things that I find the most interesting and the most fun. If you search Regge, the keyword Regge and inspire, you'll see on the side this sort of graph which shows you the distribution of papers published that have this keyword in them as a function of the year they were published, characteristic shape. And this kind of timeline will give you 3 different kind of eras that I will talk on the theme and give you kind of the main points that I want to point out. First, you'll notice obviously this big hump. The beginning of this is this seminal paper by Regge, the guy in the title, in 1959. And this huge hump was this kind of explosion of interest in this sort of theory and how we can use it to study the then unknown dynamics of hadrons and strongly interacting particles. In particular, this area is known as kind of the S-matrix bootstrap, the original S-matrix bootstrap. And I'm going to talk about kind of the important findings of these 2 guys, which are Jeffrey True and Stephen Frauci. After that, you'll notice that the hump kind of declines very rapidly. There's a very simple explanation for that as we discovered QCD. Here at the very top of the peak, Gell-Mann proposed the schematic theory of quarks and gluons. Eventually, this was validated in the parton model at DIS by teams in SLAC. And then kind of the final nail in the coffin for the bootstrap was the discovery of asymptotic freedom and the fact that we can use perturbative QCD as a dynamical theory at high energies. The third kind of era that I want to point out is where I come in. So you'll notice that I enter the world somewhere around here, but in physics terms, I enter here in the blue when I joined the JPAC collaboration in my doctoral studies at Indiana University. And of course, this past December, I'm joining you guys here at ECN. What I want you to notice is that this blue, where my research comes in, is entirely contained within the red. So I've always lived in a room, in a world post-QCD. And so one thing to kind of keep in mind is why a lot of the things that I talk about, which were developed in the 60s, some even before in the 50s, why it's important or useful to look back at these old theories, old techniques that were largely abandoned by large parts of the community, and how they can help us study hadrons and phenomenology of QCD today, right? For the record, S-matrix and S-matrix theory now has kind of this brand new life, and the word bootstrap, for example, has a brand new life in modern theories of conformal, axiomatic QCDs, QFTs, and things like that. I'm not going to be talking about any of that. I'm going to be talking about exclusively applications to hadrons. Later this summer, we have Dr. Cordova joining us, and she's a specialist in S-matrix bootstrap in the modern sense, and you can hear more about that, I'm sure, from her. So first, let's make sure that we're kind of on the same page. What are hadrons? Hadrons are kind of this spectrum of strongly interacting massive particles that were discovered. Well, the first one, of course, was the proton, discovered in nuclear structure, as well as the neutron, which are very similar, and these have been known since the early 1900s. And then in the 40s, studies with the cosmic rays discovered also lighter hadrons called the pion and the kaon. But the real kind of interest or the real kind of explosion in the complexity of the hadron spectrum came in the 50s when the first particle colliders came online. So after particle colliders came online, these kind of massive, strongly interacting, so the strong interaction of them comes from the fact that we call them strong interacting comes from their large interaction cross-sections. For example, a typical proton-proton elastic cross-section is 9 orders of magnitude larger than the typical cross-section expected from electron scattering. And there is a large spectrum of excited resonance states that couple to other hadrons and decay very quickly. So because they decay, we can't see them, we can't hold them in a bottle. Instead, we can only see them as these bumps in the spectra of their decay regions. And of course, since then, we have kind of 50 years of experiments and increasing energies. And now the modern PDG lists over or almost 1,000 pages of different listings, masses, decays, et cetera, of these different hadrons. So in those 50 years, we've learned a lot about them. We know, for example, that these are composite particles. They're an emergent phenomena that comes from a more fundamental theory. That fundamental theory is QCD. It's a relatively simple or deceptively simple theory. You can write it in one line in terms of quark fields and gluon fields. Subsequent studies and high energy experiments, for example, the LHC, have given us really precise measurements of things like the masses of these quarks and the fundamental structure of gluon and quark dynamics. So does this mean that we really understand hadrons and we're done and we can move on to bigger and better things? Well, not really, because all of the power of QCD and the high precision predictions and descriptions of QCD dynamics come in the perturbative or high energy regimes. As we move down to lower and lower energies where the hadrons become relevant or where the hadrons live, the coupling constant becomes large and all of this sophisticated framework of perturbation theory no longer works. And so that means that a lot of our physics that is well motivated in terms of fundamental theories, in terms of gauge theories, et cetera, cannot explain some of the more interesting aspects of QCD, such as the confinement of the quarks, the dynamical mass generation of most of the observed matter in our universe, and also related things like chiral symmetry breaking. We don't really have modern toolkits to address, well, we do, we have models, but we don't have a complete, rigorous, provable solution to QCD at low energies. If you're interested, of course, to give you a scale of how important and how difficult this sort of problem is, in the year 2000, a bunch of physicists, including several Nobel Prize winners, sat down and thought of the 10 most important open questions in physics to solve in the next millennium. The 10th one, of course, is how do we understand QCD from first principles, from the dynamics of quarks and gluons. Closely related also, of course, is the Millennium Prize of solving the mass gap or proving the mass gap in Yang-Mills theory. And so, of course, if you really want to become, extraordinarily famous, you just need to solve low-energy QCD. You'll probably pick up a Nobel Prize, $1 million from the Clay Institute, and likely a Fields Medal as well. More recently, in the last 20 years or so, we're also reaching kind of a new era of QCD. Modern experiments since 2003 have picked up or have noticed a lot of signals, a lot of resonance states that seem to point to structures that are beyond the conventional quark, anti-quark, or three-quark states that we kind of have seen and have studied for 50 years within QCD. So these, as I said, these are short-lived. We don't see them in detector. All we see is bumps. So for example, this is the famous X3872. This is kind of the most famous of these and the one that started this whole business. You have this peak in a decay particle spectrum. From this picture, how do you tell what's the internal structure of this in terms of fundamental constituents like quarks and gluons? Is it a tetraquark, 4 quarks bound by gluons? Is it something more complicated like a hadronic molecule? Or is there gluons that are active in the valence structure of this thing? We now, even though we have all this machinery, all this understanding within QCD, we lack really a complete description of not only normal hadrons and baryons, but also the extent that these sort of more exotic signals can tell us about the dynamics of quarks and gluons. So how do we take pictures like this, bumps in spectrum like this, and test different models, different descriptions in terms of QCD? One thing before I go into that is, of course, also that these are not, so these two are not the only ones. This is not an isolated incident. The fact that there's kind of exotic candidates, there's quite a lot. So here, all the green ones are the normal predicted QQ bar Charmonia. Everything else that is not green is an exotic candidate. So we really have a lot, we have a kind of this new zoo in our hands in terms of the XYZ particles that we really want to understand. So, as I said, we have all these bumps. How do we talk about them? How do we describe them? And how do we use them to test a fundamental theory if we don't have a first principle solution to their spectrum? Well, it turns out this is exactly the same question that people were asking themselves in the 60s before we knew about QCD at all. There, they also had a ton of experiments coming online. They had a lot of data. And they also wanted to be able to talk about this in a way that they can test, for example, whether QCD is the right theory, whether some chirally motivated pi nucleon field theory is the correct description, et cetera. And so because of that, that's where the S-matrix originated. So the S-matrix program is a top-down approach to physics. So instead of assuming, for example, the potential or some sort of dynamical microscopic theory, and then moving up to calculate scattering amplitudes to test against experiment, you do the opposite. You start with the experiment. You start with physical observables that you can measure, and you build kind of a language of general scattering amplitudes, which you then work backward. You fit to the data. You use those and interpret the features of those amplitudes to look for the dynamics in reverse. And so you start with data and work down backwards into the microscopic dynamics. The fundamental kind of object of this, of course, is the titular S-matrix. This is a quantum operator that instead of doing kind of a microscopic interactions in steps, does the full scattering event. For example, here we have two particles entering from the right and exiting to the left. This scattering event in this red blob happens in one step through this matrix S. That's the fundamental kind of defining feature of this S operator. And so from there, from that starting point, you can now input all of the kind of physical properties and things like that, concepts that you want to have in a physical theory, and see what structure emerges from them. In particular, for example, you have rotational invariance. Physics doesn't depend on how you define your coordinate system, and that lets you expand your scattering amplitudes into partial waves. This will be a central expansion that I'll talk about in the next several slides. And then you have other things. For example, causality. This one is also particularly important. Causality, which, events in the past must happen before events in the future. This implies actually a very complicated, or not complicated, a very non-trivial structure of scattering amplitudes when energies are allowed to be complex. So experiments, things that we can access in the real world, things that we can touch, obviously only live at real energies. So for example, this picture, S is the energy variable. This blue line is the real line above threshold. So this is physical scattering appears on this blue line. I cannot go to an experimentalist and say, please scatter these 2 electrons at an energy of 1 plus 2I GeV. This doesn't make physical sense. Oops. Okay. Okay. Well, hopefully that doesn't happen again. So as I said, we can't do physical scattering events in complex energy, but causality, this physical principle, actually tells us that our scattering amplitudes, the mathematical structure of this function FL of S, must still be valid at complex energies. So I should be able to take this physical amplitude, plug in S equals 1 plus 2I, and still get a reasonable result at the end. This has important consequences for theories with bound states, which of course is what I'm talking about. In bound states, the kind of elementary language, the fundamental language of at complex energies. If I take data such as like this, experiment, I can fit to here and then use principles like analyticity to go to complex energies, and I find the point where there is a pole, and this gives us the fundamental language of resonances. This gives us the mass, the width, and the couplings and the spin. These are basically the kind of, not the ideal, the basic immutable elements or properties of a resonance. And these are the things that we want, because once we get these, we can test how these things are related and look for dynamics. So everything that I said in the previous slide happens for both relativistic and non-relativistic theories. But when you move to relativistic theories, which hadrons are relativistic, you have an additional property which becomes also very non-trivial and complicated. It's crossing symmetry. So if you've taken a class of QE, you played with Feynman rules and set up amplitudes with Feynman rules. Crossing symmetry comes out for free when you do because of Lorentz covariance. But in the language of the S matrix, crossing symmetry means that we need to be able to describe all of the different reactions, particle, antiparticle interactions. So for example, if I take this C particle and exchange it with this B in the initial state, this gives us the U-channel process. All of these different, and also, for example, things like decays, all of these different scattering amplitudes, these are potentially physical processes that happen in nature, must be given by the same function. This is kind of the statement of crossing symmetry. So here in kind of a seminal paper by Sten Mandelstam, he introduces these Mandelstam variables, very famous, ST and U, which gives us kind of the description of all of these different reactions in terms of energy variables. I'm going to move it every few minutes just to make sure it doesn't happen again. And so now when we were looking at our expansions in different states, we can write our partial wave expansion in either the S channel in terms of a scattering angle in the S channel or a scattering angle in the T channel in the T channel reaction. Crossing symmetry means both of these should be valid, exact reconstructions of the full scattering amplitude. This is kind of okay, fine, we have all of this structure and we have extra things that we have to constrain our amplitudes with, but really this also becomes a question of dynamics once again when we have bound states, because if you look at a space-like exchange, so an exchange in the T channel, for example, vertical, where this momentum transfer is negative, then the corresponding scattering amplitude of this particle exchange resembles very closely the Yukawa potential in momentum space or in energy space. So because of that, there's a hint that crossing symmetry gives us a way to define our scattering amplitude dynamics without needing a microscopic theory. If, for example, if you have a resonance in the S channel and you want to say what is the dynamics that's binding this resonance in the S channel together, all you need to do, according to crossing symmetry, is look at the spectrum of particles, the forces, the potentials, in the cross channel, and then you work backwards. So if you know, for example, the T and the U channels, you can get the spectrum of the S channel. This was very, very exciting. It's like, okay, cool, we can solve hadron spectrum and get things like scattering amplitudes without needing a microscopic theory, but there was a problem. There's this famous result by Lehmann that this sort of expansion only converges, it only makes sense within a finite region in complex angles. So here you'll notice that there is you can interchange energies and angles freely. What we said in the last period, we must have analyticity in S because of causality. Because of crossing symmetry, this also implies that we need analyticity in angles as well. That's not a problem here because the Legendre polynomials are analytic. You can put a complex energy is fine. But if you look at this entire sum, the entire f of S, you're limited in what angles you can do. Basically, you can't go too far above the physical region in this angle before this series converges, is the structure of Lehmann. So that means that our understanding of crossing symmetry was kind of incomplete at this point. And it was fixed just a year after this was pointed out by Regge. So here I'll finally be able to introduce Regge, which is the extension of this sort of expansion into the complex energy plane. So here I'm noticing that I'm taking a little bit of time, so I'll breeze through this. This is a little bit technical. I'll want to give you just the main ideas so that we can move on to applications. Basically, using fairly general principles of analyticity. Again, this is this core principle of causality, related to causality. You can prove, or Tulio Regge proved, that the analyticity needed in angles as well as energies also improves something strange, which is analyticity in angular momentum. And so just like you can write this as an expansion over physical integer angular momentum L, this is an incomplete picture because it only converges within a specific region. The more complete description of scattering amplitudes involves taking your partial waves as well as Legendre polynomials into non-integer complex angular momentum. That sounds strange. What is the polynomial? For example, what's the Legendre polynomial of 1 plus 2i? That doesn't make physical sense, but mathematically you can do it. It's called analytic continuation, and you can write Legendre polynomials in terms of hypergeometric functions, and you can get a number that makes reasonable sense. You can also do the same for partial waves, so this is perfectly reasonable. And when you do this, remember, we want to learn about the dynamics. And so we want to find poles. We want to start with an amplitude that has poles in the T channel and then move them over to the cross channel, to the S channel, to see how that influences the bound states there. When you do that, you'll notice that the poles in the T channel in this continuation will move away from the energy variable T, or they still exist in the T plane, but they emerge as poles in the complex angular momentum as well. And so the big defining, game-changing idea that Regge showed is that resonance states have this dual description in terms of poles in energy as well as poles in angular momentum. And so again, physics, despite physics living and existing or the physics we see existing at integer real L and real energies, the demands of fundamental scattering theory require us to be able to extend both of those variables arbitrarily. I'll just very quickly, this is kind of again, this was a fundamental idea and it reached a lot of interest, but it was eventually kind of replaced by QCD, and so now, I'm kind of a practitioner of this sort of, these sorts of tools, and there's constantly these misinformation or misunderstandings of Regge theory as a fundamental theory or not. Everything that I said here, I breezed through it because of time purposes, but everything I said here, none of this have I mentioned any sort of dynamics. What theory am I talking about here? It turns out I'm talking about any theory of relativistic quantum mechanical scattering. QED has this structure. QCD has this structure. Some extra secret third theory that you want has this structure. This sort of structure in angular momentum plane is fundamental to scattering theory as a whole. And so, now we're kind of combating this sort of idea of, in constant referee reports, we get this sort of notion that, oh, you're using a phenomenological onsets. That's not true. But anyways. Before I go here, one thing, so here the poles of resonances in the cross channel move onto the angular momentum plane. A core object in doing this is this function alpha of t. So this alpha of t is called the Regge trajectory. And if you take this sort of term and you partial wave project it back onto physical integer L, you'll get a term like this. And so here your pole is of the form L minus alpha of t. If you take this form, this pole must match, because it's the same function to the poles we were talking about in energy. This alpha of t is a function of energy, and so it is a moving pole in the complex energy plane. So it's not just a fixed, resonances in energy are a fixed pole at some mass and some width. In the angular momentum plane, they move as a function of energy. Moreover, this sort of term will project onto every possible L that you want with the same trajectory alpha of t. And so that means this alpha of t has a special property that at any integer L that it can realize, it will manifest a pole. And so that means the same moving pole can be responsible for a potentially infinite family of different resonance states that are all coming from the same dynamics. So using that kind of pole observation, a critical observation was made by Chu and Frauchi in 1962, which is if you take the hadrons that were known at the time and you plot them spin on the vertical axis and mass on the horizontal axis, they seem to obey pretty universal, almost linear types of shapes. And you say, okay, well, look at this picture. They have two points and they've drawn a line. How physics is this, right? This is kind of hokey, it's a guess. Well, 50 years later, we have a lot more resonance states, and we can see that, yeah, actually it is. It's incredibly linear in approximation, for example. And so this is telling us that the dynamics of these different hadron states, because they lie on the same trends, they lie on the same Regge trajectories, must originate from the same dynamics. In addition, this also gives us kind of a more natural way, or gives us a very natural way to organize and see the types of symmetries and the types of relations among the hadrons themselves. So here, for example, if you take a bunch of, these are the baryon sector. If you take a bunch of widths and masses and you plot them against each other, you just see a blob. There's no structure here, again. But you take the mass up here, or the width down here, and you plot them against their spin, you once again see this kind of emerging structure, this emerging pattern of the different Regge trajectories that sort the different hadrons among themselves with different quantum numbers. For example, this is unnatural parity, natural parity, and things like that. And so this was very early indication in the early 60s of the dynamics that was inherent to this sort of spectrum. In particular, the fact that all of these different resonances all seem to lie on these lines points to they're all coming from the same dynamics. I said that. And so that means that, let's go back here. This is the neutron. The neutron is right here, or the proton is right here. The proton lies on the same trajectory as this excited neutron. It's pretty, we're pretty sure that this excited neutron is not a fundamental particle because it decays, it doesn't live very long, et cetera. And so that means if this is not a fundamental particle, neither can the proton be. And this was a very radical idea in the 60s when Geoffrey Chu, for example, kind of made this claim that within this purview, with Regge theory and this S-matrix framework, we cannot claim that any of the hadrons are particularly elementary because they're all on these trends. They must all be, either they're all elementary and we have infinitely many elementary particles, or they're all composite. And this was 2 years before, for example, Gell-Mann proposed his composite theory of quarks and gluons. In addition, for example, a lot of work went into understanding even more kind of the emergent spectrum in terms of forces. And this famous model was proposed by Veneziano, which actually was the first string theory. Leonard Susskind famously analogized this amplitude as giving the spectrum of two quarks, or a quark and antiquark, connected by a string. And this actually explained, for example, the structure, the fact that they're lines. As you move up a line, you're exciting the orbital excitations of this stringy system. And as you move down to one of the parallel lines under it, you're exciting the radial system. And so this, of course, eventually developed life of its own as string theory, but this started to understand this sort of L-plane structure of hadrons. So now let me see how I'm doing on time. I should hurry up. This is all in the past, and so now I want to talk about what I do and what I plan to do with you guys, for example, if any of you are interested. I have 3 applications. We'll see how much we can get through. Maybe I'll skip the middle one. The first one is high energy phenomena. The structure that we saw previously, this sort of big expansion that we did by analytically continuing our scattering amplitude into the J-plane or the L-plane, has this big, ugly integral, which is very difficult to model because it requires you to know your scattering amplitude, your partial waves at complex energy. I mean, a complex L-plane. Like I said, this physics tells us we need to be able to account for this, but what does it actually make a model for it? Very, very difficult. But you can show that at very, very high energies, this is very good because this is kind of a fundamental form which only depends on two things. This beta function, which is just a coupling. You can estimate this using a scattering, for example, decay widths or interaction models. And alpha of t, which is your spectrum. You know your spectrum, and so you just make a line and you do this sort of thing. And so this sort of form is called the Regge exchange amplitude and is a fundamental kind of tool in modeling high energy, soft production processes, and it's constantly used every day. So one application, for example, that I've been very involved with is the potential to study those exotic hadrons that I mentioned several slides ago in production processes. So here, for example, this is a photoproduction process because it's a photon beam incident on a proton target. This creates some sort of exotic resonance in this top vertex, and the bottom vertex is kinematically separated because of the properties of our Regge amplitudes. And so here, this provides, Regge phenomenology provides us with a really lightweight starting point that's still based in fundamental first principles to estimate the cross-sections that we might expect for this sort of reaction at future facilities. And I've now been in led 3 different papers to produce predictions for these sorts of reactions for the facilities in the future. But despite these 3 papers, there's still kind of a lot to do. In particular, for example, right now, the EIC, the EICC in China, the JLab 22 upgrade in the United States, as well as now a proton-proton facility in Fair, are in the early stages of being designed and being built. And so there's a lot of simulation and detector efforts being put in, which require theory input. Obviously, if you want to design a detector so that you can capture all of the products of a reaction, you know, for example, where we should expect these the reaction particles to be, et cetera. And for that, we need reaction models and we need predictions. In addition, there's also still a lot of background processes and other more exotic topologies that we want to consider that we can handle within our Regge type framework and provide for these facilities. So that's for this. This is also kind of the classic application of Regge theory because of this sort of expectation of asymptotic Regge pole dominance. And so here, this is also bread and butter for the past 50 years of Regge phenomena. People have been doing this forever. Maybe more novel or interesting applications also is how we can use Regge theory, which is conventionally often thought of as just a high energy parameterization or theory, to constrain the dynamics of interesting low energy amplitudes. In particular, the Regge structure of the L-plane and analyticity allows you to derive a lot of consistency relations. For example, most famously are these that are called finite energy sum rules, or FSRs. Why people don't say FESRs, they say FSRs, I don't know. But these sorts of consistency relations relate the high energy Regge behavior on the right-hand side with averages or integrals, moments of the low energy amplitude on the left-hand side. And so this was originally proposed in the 60s as a way to provide, treat these as dynamical equations. You put some inputs on the left-hand side and you solve for the right-hand side. This started the original Bootstrap program and ultimately didn't really work. But instead, these are not treating them not as dynamical equations, but as constraint equations to impose the non-trivial constraints of analyticity can allow us to basically diagnose if we have a low energy model, compare it with data, and see if there's some sort of insufficiency or incompatibility with fundamentals of scattering theory, for example. One very, very important process that stands out because of these sorts of because of this, first of all, we understand the high energy behavior a lot. There's a lot of data in the high energy behavior. There's a lot of interest in the low energy, but we have very little data and we have a lot of models. This is photo production of the Jape psi near threshold. And this has been proposed for a lot of reasons. It's a signal channel for hidden charm pentaquarks. So pentaquarks potentially could be found in this reaction. A lot of perturbative QCD people claim that this is also a direct probe of the gluon gravitational form factors of the proton and other fundamental quantities such as the mass radius of the proton, the generalized parton distribution functions, etc. And the point is, there's a lot of people proposing different models, claiming different things. For example, in perturbative QCD, you say, oh, it's dominated by scalar gluon operators, a spin 0 exchange of gluons. And then another group will say, no, actually, it's a spin 2 exchange of gluons. It's more like a tensor Pomeron. You have actually some collaborators of mine in Bonn claiming, no, it's actually not gluons at all. This is dominated by heavy meson exchanges. Etc. And obviously there's also extra people saying, no, there's pentaquarks, there's not pentaquarks, things like that. Frankly, there's a lot of different models. A lot of them are trash, a lot of them are not trash. And that doesn't, there's a lot of uncertainty into what's the actual dynamics of this process. But even then, it doesn't stop people from making these bold claims and, for example, getting into Nature claiming that you've measured the gravitational form factor of the proton. So, for example, I attempted to, and my collaborators, we attempted to sort through all the garbage and see how much we can actually tell from the data in a model-independent way. We did this not with a Regge model. This was it's called a K-matrix model, and we did this. It's based on expansion near threshold, and we want it to be as model-independent as possible. That comes, of course, with a very, very high cost, which is if you don't have any dynamical assumptions, you don't have any constraints other than fundamental ones. And so any parameter that can be free kind of needs to be free. And so the cost that we paid for having model independence is a lot of free parameters, and we simply don't have enough data to make any conclusive statements. So basically our analysis really was the most rigorous and the most model independent analysis out there, but our conclusion unfortunately was we still don't know. The model, the data bars, for example, you can see here, this is our integrated cross-section. The error bars in the data is still large enough that all of the different possibilities that I had here on this page are still possible. So we still don't know. So we have several options. One of them is wait 5 to 10 years for more data to be taken, and we certainly are doing that. But also, we don't necessarily have to just sit and wait. We have this Regge theory. We have a lot of high-quality data in the high-energy behavior. We can see how these sorts of analyticity constraints inspired by Regge phenomenology tell us about all the different low-energy models, and can we, for example, dispel some or confirm some and things like that. And so this is something that I want to realize in the near future. Oh, okay, I sped up, and now I've sped up a lot more, and so I'm almost done, but that's okay. The final application is the one that I find the most fun, because this is just sitting at my desk and playing with mathematics, is thinking of how to really extract resonances directly. So again, resonance exists in terms of poles and energy, but they're part of this more fundamental structure, which is they lie on Regge trajectories. And so we can learn more by extracting the Regge trajectories themselves instead of individual poles. One way to do that is to think, okay, let's create an amplitude that has all of the different constraints that we want in terms of Regge trajectories and fit this to data. This is, top-down sort of application. And so I outlined a few of the more important ones, the constraints up here. So these were in the S matrix thing. But for a simple process like pi-pi scattering, this is the simplest hadron process you can think of, you actually have a lot more restrictions or constraints that you can write down that you should expect any reasonable scattering amplitude to follow. So for example, here, I showed you the pictures of the Regge trajectories, the Chu-Fauci plots. They look like lines. Annoyingly, you can actually prove from principles like analyticity, they cannot be lines. These are actually much more complicated functions which follow their own dispersion relations, and they're bounded above by, for example, square root of s. And so you somehow need to make a complicated model using these sorts of equations for alpha of s, which looks like a line and fits through the line as well as other data. More than that, also you have, for example, perturbative QCD expectations. Like if you go at fixed angle high energies, you should expect a scaling law type behavior and things like that. So can we think of a model that satisfies all of these? Well, let's look at some of the more famous or more widely applied and widely used models and see how they fare up. So in the JPSI, I mentioned we use the K-matrix model. This one is very, very widely used because it's very simple and very flexible. It's unitary by definition, so you don't have to worry about things like unitarity. But, for example, it doesn't satisfy crossing symmetry. It has no in fact, it has the wrong structure in the angular momentum plane because this has a discrete, finite number of partial waves. It has nothing to do with trajectories, etc. And so that's what that is. I also mentioned the Veneziano amplitude. This is a very, very famous amplitude that started the whole of string theory. How does it line up? Well, one of the things that makes this amplitude beautiful is the fact that it ignores unitarity in its entirety. All of the resonances are assumed to be stable particles, and so that automatically makes it unable to describe any physical, realistic scattering process. In addition, it actually requires linear real trajectories, which, like I said, violate analyticity. It also cannot incorporate different trajectories to accommodate, for example, different families of hadrons that can contribute to the same scattering amplitude. Also no scaling behavior, et cetera, et cetera. So this one also fails. Well, last year at Bonn with a student that recently graduated several months ago, we came up with a model. It started originally as a toy model. Let's take a bunch of poles in the L plane and find a nice little parameterization that we can play with and investigate the properties of. Well, what started as originally a toy model, we kept looking like, oh, well, does it have scaling behavior? It does have scaling behavior. Does it have Regge behavior? It does have Regge behavior, et cetera. And as it turns out, we clear most of the restrictions that we set out for ourselves in terms of fundamental restrictions for this pi-pi scattering. In particular, this sort of summation can be done analytically. So the continuation to the L plane can actually be done in closed form, again, in terms of the hypergeometric function. And the only kind of the two caveats, one is that it's not unitary by construction. Unitarity actually requires us to solve some pretty gnarly nonlinear integral equations, but it's doable. We did it for a test case, and we want to do it for more complicated cases. So we have this new model. It seems to be kind of very, very well constrained. It has all of the properties and all of the behavior we want. Disease-free is crossed out because we do have additional cuts that we kind of shove off into the high energy behavior. This is not necessarily the wrong, well, it's basically just an effective thing, but it's controllable is the point. So we have this model. It's very nice. It has all of these nice properties. Let's apply it to data and see what we can learn. We applied this to pi-pi scattering in isospin 0 and isospin 1. So these are the lowest lying. The easiest case is this rho meson. This is the prototypical rho trajectory. It's the line. In fact, here you have 0.5 plus 0.9 s. This is the phenomenological line that I showed you before. This is Chu-Frauchi's result. We impose low energy unitarity. And so we fit this shaded region, and we can extract this Regge trajectory for the rest of the spectrum. And what we find, first of all, is you can describe the rho line shape very well. The scattering amplitude, or the partial wave, is described very well. And when you move outside of the fit region, for example, in the time-like region, this is this Yukawa-like regime where the particle is exchanged to the T-channel, you go through all of the data points of some pi-n scattering data. This is not included in the fit. This is just what came out as a result. And so this shows really the non-trivial and very powerful constraint of unitarity on Regge amplitudes when you have something that can satisfy both simultaneously. Hints that the non-linear deviates. These data points seen in experiment also. So this was the easy case. This is the test case. This is well known and well studied and reproduces more. Now, something weirder, which is the sigma meson. Pi meson. we find is a completely different shape for the sigma meson than we did for the rho. In particular, this it goes. So instead of differences in dynamics, obviously, that you can see in the form of rows or rows. This like shape where it goes up and goes down means that the sigma meson does not have any associated excitations at higher angular momentum or radial momentum, for example. And so this points to the sigma being a little bit more of an extended object, and the dynamics of sigma exchange really is like a non-relativistic Yukawa-like potential instead of a relativistic Reggeon potential. And so that was the third. And just very quickly, the future of this sort of project, we did just an initial numerical study of this. We want to do more in-depth numerical studies, as well as this is very exciting, and maybe we can use this for more powerful, more complicated reactions, things with spin, decays, productions, etc. And that's the type of things where this project is going. So now, finally, the summary, of course, is we want to understand non-perturbative QCD. Despite knowing about QCD and being fairly convinced that it's the correct theory of hadrons, after 50 years, we still don't have a true solution to non-perturbative QCD. The best window into non-perturbative dynamics is the hadrons themselves, and so we want to study them to use their properties to test microscopic models. The fundamental language that we do that with, of course, requires things like S-matrix theory, and Regge theory in particular is a key part of it. So the non-trivial constraints of Regge theory help us constrain the types of amplitudes we can do and extract a lot more correct physics from our data. And we can use those to test different models. Thank you.
Thank you, Daniel. So just before, sesión para YouTube. Damos las gracias y nos vemos en el próximo coloquio aquí de investigación. So in the meantime, you want questions in English?
Lo que sea.
Okay.
Depende de responder en inglés, pero.
Tenemos tiempo para varias preguntas, pues.